Good day, everyone. For today's topic, for today's video, ang ating topic is Fundamentals of Fluid Flow. Daanan na natin ito siya, pero ang aking i-present lang is yung mga video presentation galing sa YouTube. Makatulong itong mga videos na ito dahil mas ma-represent or mas ma-visualize ninyo yung mga problem or topics and then yung mga definitions regarding sa fluid fundamentals of fluid flow. So let's start. Okay, so let's play the video.
We discussed the fundamentals of fluid flow. This lecture tackles the flow rate, the energy and the head of fluid that is traveling inside a pipe. We will be discussing also here the efficiency of pumps and turbines. And the last part of this lecture is about Bernoulli's equation. So let's start. So let's define discharge, or also called as flow rate. Let's say we have here a pipe where fluid is traveling inside that pipe. We define the discharge or the flow rate as the amount of fluid passing through a section of a stream in unit time. So let's say this is your section of the pipe. So the amount of fluid that is passing through that section, which is the volume of that fluid per unit time, which is the time. Okay, so it means the amount of the rate of flow of the liquid inside the pipe is your discharge, or we can express that as the volume per unit time. So our symbol used for discharge or flow rate is Q, with a unit of in SI unit, which is in cubic meter per second, or per hour per minute, depending on the required. Now, we can also define the discharge or flow rate if we have a given cross-sectional area of a pipe and the equivalent average velocity of the liquid that is traveling on that pipe as the product of the cross-sectional area and the velocity will be equivalent to our flow rate, because the area, given that we have a unit of square meter and a velocity of meter per second, it will give us a value of cubic meter per second, which is equivalent also to the unit of flow rate. Okay, so either we have volume per time, or the discharge or flow rate is equals to cross-sectional area times velocity. So let's discuss Reynolds number. Reynolds number is one of the bases of the resulting value for the Reynolds number is the basis on to what type of flow that is present on a pipe. So Reynolds number has a formula of Vd over nu, or it is also equals to rho Vd over mu. So the velocity of flow is V, d is the inside diameter, rho is mass density, mu is kinematic viscosity, and mu is the dynamic viscosity. So depending on the value of the Reynolds number, we can identify what type of flow it is in the pipe. So we can say that we have a laminar flow when the paths of the individual particles do not cross or intersect. So let's say we have here a liquid passing through this pipe. Okay, so all the particles move on the same direction. Okay, they are uniform in direction. So, by many careful experiments to commercial pipes of circular cross-section, the flow is laminar when the computed Reynolds number, or RE, is less than 2,100. So, using this formula, if we have computed less than 2,100 for the value of the Reynolds number, it is laminar flow. On the other hand, we have a turbulent flow when the flow is said to be turbulent when the path lines are irregular curves and continuously cross each other. The paths of particles of a stream flowing with turbulent motion are neither parallel nor fixed, but it aggregates to forward motion on the entire stream. So the value for the Reynolds number should be greater than 2,100 for it to be turbulent. Okay, so that's it. We have laminar and turbulent flow. Now for continuous flow, um, given that we have a pipe with varying cross sections, so by principle of conservation of mass, continuous flow occurs when at any time the discharge Q at every section of the stream is the same. So in a liquid that is flowing in a pipe that has a varying size or the cross section, the value of discharge is always the same at any point. Okay, so it means that at point 1, point 2, point 3, we have the same values for its discharge. Okay, so it will give us each value even though the cross-sectional area are not the same. Okay, the discharge are always the same. For incompressible fluid, this is our equation, and for compressible fluids, we just put the pressure. Okay, we multiply the pressure on the product of the cross-sectional area and the velocity at each section. So example number 1, we have to determine whether the flow is laminar or turbulent if glycerin at 25 degrees Celsius flows in a pipe with 150 mm inside diameter. The average velocity of flow is 3.6 meters per second. And given the mass density of glycerin, which is 1259 kilograms per cubic meter, and the dynamic viscosity is 9.6 times 10 raised to negative 1 Pascal second. Okay, so let's solve this problem. The given are the temperature, we have 25 degrees Celsius, the inside diameter of the pipe, that's 150 mm inside diameter, average velocity V 3.6 meter per second, mass density rho 1259 kilograms per cubic meters, dynamic viscosity mu 9.6 times 10 raised to negative 1 Pascal seconds. So let's solve this using the formula for the Reynolds number, which is equals to rho phi d over mu, since we have a given dynamic viscosity. So the given mass density is 1259 kilograms per cubic meters. The velocity 3.6 meter per seconds. Diameter 150 mm. We convert that as in meter. So divide 1000, that's 0.5 15 meters. 0.15 meters for us to have a consistent unit of meters on all the given values. And dynamic viscosity 9.6 Pascal second times 10 raised to negative 1. Pascal is in Newton per square meter. Okay, so that's Newton per square meter. Newton per square meter second. So if we still want to convert Newton, that's equivalent to kilogram meter per second squared. Okay, so let's rewrite the unit of kilogram meter per second squared. So let's check what unit we will have in this problem. Okay, so based on the given units, all the units will be cancelled out. Okay, so we will have a unitless value for Reynolds number. So let's now compute. So just make sure that all the units that we use here in this equation are consistent, which is in kilogram, meter, and in seconds. So we have 1259 times 3.6 times 0.15 over 9.6 times 10 raised to negative 1. Okay, the Reynolds number is 708.1875. Okay, the Reynolds number that we have computed is less than 2100, which is an indication that this flow is laminar. So the type of flow of the glycerin in a pipe, in a 150 mm pipe, is said to be laminar. Okay, so that's how you solve the Reynolds number. Example number 2. Compute the discharge of water through a 75 mm pipe if the mean velocity is 5 meter per second. So given is the diameter of pipe, which is 75 mm. Mean velocity is 5 meter per second. So flow rate Q is equals to area times velocity. So area is equals to pi d squared over 4 if we have given diameter. But we have to convert mm in meters so that we will have an equivalent value of cubic meter per second for the discharge. So divide this by 1000. The diameter will be 0.075 meters raised to 2 over 4. So computing the area, cross-sectional area, that's 0.075 squared over 4. Okay, 0.0044. Or we can directly substitute that class here. Area, which is pi times 0.075 meter square over 4. Then we multiply that by the mean velocity of 5 meter per second. So the answer is equals to 0.022 cubic meters per second. Okay, that's the discharge. Next, the discharge of air through a 700 mm pipe is 6 cubic meter per second. Compute the mean velocity. So this time we have a given discharge Q, which is 6 cubic meter per second. The insert diameter of the pipe is 700 mm. Compute the mean velocity. So again, Q is equals to AV, but what is required is the velocity. So divide both sides by area. So we have the velocity of Q over A. So we can directly substitute the values here. We have 6 cubic meter per second. And for the cross-sectional area, we must convert first the diameter of, this pipe, which is in mm. So divide by 1000, that will be 0.7 meters. And for the cross-sectional area, we have pi d squared over 4. Substitute that here. We will have d of 0.7 meter square over 4. So we directly calculate that. We will have 6 over pi times 0.7 squared over 4. That's 15.591. 15.591 meter per second. So units in meter per second for the velocity. Okay. Next problem. A pipeline consists of successive lengths with diameters of 390 mm, 310 mm, and 260 mm, with a continuous flow through the line of 300 liter per second of water. Compute the mean velocity in each size of pipe. So we have a pipeline here with different diameters. We have 390 mm for largest pipe. This is 390, it's the diameter. And this diameter of this one is 310, the smallest diameter 260. Okay, diameter 1, diameter 2, diameter 3. Let's determine here the mean velocity on each pipe. So what will be the velocity here and the velocity at the smallest. Okay, so again, using the principle of conservation of mass, the mass or the flow rate on each section are equal, because of course the amount of water that will be traveling from here is just the same. All of the water particles that will travel on the largest pipe up to this point will just be equal. So all of the flow rate are equal, making an equation Q1 equals to Q2 equals to Q3. It means that their values are 300 liter per second. Okay, so given the diameters of each pipe, we can determine the cross-sectional area, and we can also determine its mean velocity on each pipe. After that, we can compare how proportionate it is, the velocity with respect to the cross-section. Okay, so given the flow rate of 300 liter per second, let's convert that first to cubic meters per second. So conversion factor for 1 liter, okay, to cubic meter is that for 1 cubic meter, we have 1000 liters. So it means to convert this to cubic meters, that's to be divided by 1000. So we have 0.3 cubic meters per second for the value of discharge. So for Q1, Q is equals to AV, so the area at the first section, and the velocity. So the velocity is Q1 over A1, or just Q. So Q is 0.3 cubic meters per second over area 1. So the area, if we have 390 mm, so pi d squared over 4. That's 0.3 cubic meters per second divided by the diameter is 390 mm divided by 1000. That's 0.39 meters square over 4. So the velocity is 0.3 over pi d squared over 4. That's 2.511 velocity in meter per second. That's the answer for the first or the largest pipe. For the velocity at the second pipe, V2. So let's just derive that from Q equals to AV. V2 is just equals to the flow rate over the cross-sectional area. So the flow rate is just the same, which is 0.3 cubic meters per second over cross-sectional area. Let's just substitute the diameter 310 mm, convert that to meter. That's pi d squared 0.31 meter over 4. So let's just change this to 1. Okay, that's 3.975 meter per second. For the velocity on the smallest pipe, we have Q3 over A3. 0.3 cubic meter per second again, to be divided by the diameter is 260. So pi d squared over 4, 0.26 meters squared over 4. The answer is, let's change this to 26. The answer for the velocity is 5.65 meters per second. Okay, so here are your values. So as you can see, based on our calculated values, the velocity increases when the diameter is decreased. So it means that the diameter are inversely proportional with respect to the velocity. So when you increase the size of the pipe, the smaller or the slower the velocity in the pipe. But when you decrease the diameter of pipe, we will have a larger value of velocity. So that principle is used usually when we use it on our garden hoses. Okay, so on our garden hoses, usually we cover some part of the opening of the hose for us to have a stronger discharge on the hose. So it means that because when we decrease the value of the opening of the pipe, the tendency is that we have a smaller value of the cross section or the diameter, and it will result to a greater value for the velocity. So in this principle, we have already applied this conservation of mass. Okay?
Okay, so next video tayo. Okay, let's continue the video.
For energy and head of flow, usually kinetic energy and potential energy are the two commonly recognized forms of energy. But here in flowing fluid, we have the kinetic energy, potential energy, the pressure of the fluid, and other forms of energy that could be present in a flowing liquid. So usually we express the energy in terms of head. So the head is the amount of energy per Newton or per pound of a fluid. So the first type of energy present in flowing liquid is the kinetic energy. So the kinetic energy is the ability of a mass to do work by virtue of its velocity. So here is our equivalent formula for the kinetic energy. WV squared over 2G. But if we are going to express that into its velocity head, uh, since the head is defined as the energy per unit uh, per weight, we cancel out the W. Okay, so let's say we have here point 1. This is a pipe. We have a flow of the pipe going from point 1 to point 2. So if we have a value of the mean velocity at point 1, we will be able to determine the velocity head by using this solution, V1 squared over 2G. We can also determine the velocity head at point 2 if we have a value for the velocity at point 2. Okay, next, the elevation energy or the potential energy. In connection to the action of gravity, elevation energy is manifested in a fluid by virtue of its position or elevation with respect to a horizontal datum plane. So if we have a reference point or datum where we have the value, let's say that datum has an elevation of 0. Okay, so if we are going to determine the potential energy at point 1 or point 2, so we can use this equation. This is an equation from physics for the potential energy, or we have there mgh, or weight multiplied by the z distance, or the distance or the position or the elevation of that point from the datum. So we have mgz. So that z is measured from the datum going to the point where we are going to calculate the potential energy. So this is distance z. This is also distance z. Okay, z at point 1, z at point 2. So for the potential energy, for the equivalent elevation head, pressure head for that, for the potential energy, we only have Z when we cancel out W. Okay, so again, the head, elevation head or the pressure head for that particular energy is just equivalent to the energy per Newton or energy per weight. So we only have Z for the elevation energy. Next, we have the pressure energy. So a mass of fluid acquires pressure energy when it is contact with other masses having some form of energy. Pressure energy, therefore, is an energy transmitted to the fluid by another mass that possesses some energy. So pressure energy is also under the potential energy, and we have an equation for the pressure energy of W multiplied by the pressure divided by the unit weight. Okay, so the pressure head, if we will divide it by the weight, we will have the pressure to be divided by the unit weight of the fluid. Okay, so combining all the energies present on a section of a pipe, the total energy or head in a fluid is just the sum of the kinetic and potential energy. So again, potential energies are pressure energy and elevation energy. So combining the two, the kinetic and potential energy, we have the sum of kinetic energy plus pressure energy and the elevation energy. So if we are going to compute the total head, just add the velocity head, the pressure head, and the equivalent element. So usually if we are required to determine the total energy, it is referring to the total head. That's why we have an equation here for the total energy, which is V squared over 2G, the velocity head, P over gamma, the pressure head, and Z as the elevation head. So our total energy here is expressed in meters. Okay. For the power and efficiency, power is the rate of doing work per unit of time. For a fluid of unit weight, gamma in newtons per cubic meter, and flow rate of Q in cubic meters per second, with a total energy computed E in meters, which is the total head, the power watt is Q gamma E. So, substituting the values for Q, gamma, and E with these units, Newton per cubic meter for gamma for unit weight, cubic meter per second for flow rate, and meter for the total energy, we can compute the power. So that unit will be in watt. Okay? So, the efficiency usually more likely this is applicable when there are turbines or pumps that is installed in the pipe, so that we can determine how efficient it is. So to compute the efficiency, we have here output divided by the input multiplied by 100%. So what do you mean here by the output and input? Let's say this is our pipe where we installed turbine or pump. Okay, let's say pump because it's going upward. So if we computed the power at point 1, okay, that will be your input. Okay, power input. And when we computed the power at point 2, okay, that will be our power at the output. So we will be able to compute how efficient, usually we compute the efficiency of the pump, or if it is going down, the flow is going down, we use turbine. Okay, so we can compute the efficiency of that installed pump or turbine when we compute the power on the input and power at the output. Okay, so here are the conversion factors for power, from horsepower to watts, horsepower to foot-pound per second, and watt to joule per second. Okay, next. So knowing the energies present in a fluid flowing in a pipe, so we can now apply Bernoulli's energy theorem. So applying the law of conservation of energy, considering that fluid is incompressible, Bernoulli's theorem states that neglecting head loss, the total amount of energy per unit weight is constant at any point in the path of flow. Let's say in this figure we have pipe where a liquid flowing from point 1 going to point 2. So according to Bernoulli's energy equation, we will neglect the head losses. So usually these head losses are the friction in the pipe that may cause to the reduction of energy from point 1 to point 2. So the total energy at point 1 is equal to the total energy at point 2. So no head loss is the ideal condition leading to the theoretical values in the results. Again, recalling the energies present at point 1 and point 2, we have the elevation energy. So if we have here the datum, if we are going to determine the equivalent elevation head, this is distance z. Okay, and if we have here the pressure head, so the pressure head will be this one, P1 over gamma. So the pressure head, so that total distance from the pipe to that point, okay, is our reference point for our hydraulic grade line. So another, we have the velocity head for the velocity energy. So we have V squared over 2G. So that point from the hydraulic grade line up to that point is your energy grade line, reference point for energy grade line. On the other hand, we have at point 2, we determine the elevation head Z, that is Z2, the pressure head, so that computed pressure head, and the velocity head. So theoretically, according to Bernoulli's energy equation, is that the sum of this velocity head, pressure head, and elevation head on point 1 and point 2 are equal. That's why when we try to draw it here, those elevations, those pressure heads and velocity heads, we will have the same height, total height of those energy head. Okay, so if we are going to make an equation using the Bernoulli's energy theorem, we have E1 equals to E2. So again, if we include W for pressure, velocity, and elevation energy, this will just be cancelled out because all the terms have W, have weight. So therefore, our Bernoulli's equation is this one. Okay, the sum of the velocity head, pressure head, and elevation head for point 1 is just equals to the sum of those heads, of energy heads at point 2. Okay, so since here in Bernoulli equation, the head loss is neglected, but if we want to consider the head loss in the pipe, so usually we have frictional head loss, internal head loss due to internal friction, and there are other factors that may cause the reduction of energy from point 1 going to point 2. So speaking of head loss class, this will be discussed on the later part of our lecture in hydraulics. But if we are going to consider the head loss, so energy equation for that is that we will just subtract the head loss on the energy one where the flow comes from, or the starting point of the section where we are going to determine the energy, and we will subtract the head loss at point 1, and that will be equivalent to the energy at the end point, or point 2. So almost similar sa Bernoulli's equation, we will just take the sum of the pressure head, velocity head, and elevation head, and okay, so here in a Bernoulli equation, we neglect the head loss, but in reality class, there are losses in energy as the fluid flows within the pipe. So from point 1 going to point 2, we expect that there will be reduction of energy going to point 2. So most of the time we have there the head loss due to the internal friction of the pipe. So we should really consider this head loss. So how do we apply head loss, or how do we include the head loss in our computation? So in making the energy equation, considering the head loss, applying again the principles of conservation of mass, is that the energy at point 1 should be equals to point 2. Only that we have to consider the head loss. So if we are going to consider the head loss, so it means that we will subtract the head loss at energy at point 1, and that will be equivalent to energy at point 2. So the diagram for our hydraulic grade line and energy grade line looks like this. Okay, so there will be reduction in the value or the total energy of the velocity head, pressure head, and the elevation head. So that difference from energy at point 1 to energy at point 2 will be your head loss. Okay, next, when we use pumps, so usually we use pump to raise water from lower elevation going to a higher elevation. So the use of pump is basically to increase the energy of flow. So the pump consumes electrical energy, which is our input, okay, and delivers flow energy, which is the output. Okay, so again, the pump will increase the energy at point 1 in order for us to have the same energy as 2.2. Applying again the energy equation, considering the head loss. So if we have head loss here, we will subtract again the head loss and the energy at point 1 from the starting point. And also we have an additional head due to the pump. Okay, so the head is an additional, the pump gives us an additional head at point 1. So our symbol for that head is HA. So it will be added at the energy at point 1, and that should be equals to 0.2. So by the way, class, speaking of head loss, this will be discussed later on our lectures in hydraulics, but not in this lecture video. So this will be on the later part of our lectures in hydraulics. So again, applying again the, or taking again the sum of the velocity head, pressure head, and the elevation head, and including the head due of the pump and the head loss, this is plus, and this will be our equation. Okay, considering the head due to the pump. Okay, so to compute the output power of the pump, so the additional head that we have will be multiplied to the flow rate. Okay, the flow rate at point 2, where but of course the flow rate at point 1 is just the same at point 2. So the flow rate on the pipe, and the unit weight of the fluid, and H of A. So for the turbine, okay, so again, the pump, the purpose of the pump is to increase the energy from point 1 going to point 2. On the other hand, the purpose of turbines, when we use turbines, is that we will extract flow energy from the fluid that is flowing in the pipe, and convert it into mechanical energy, which in turn converted into electrical energy. So the purpose of turbine is for us to generate electricity. So Usually, turbines can be found on dams or hydroelectric power plants. So, as liquid flows from point 1, that energy from point 1 will be deducted or reduced by the energy due to the installed turbine. So it means that the energy at point 1 will be subtracted by the equivalent head on the turbine. So our symbol for that is HE for the head of the turbine, and that will be equivalent to our energy at point 2. So it means, applying again the energy equation, uh, we have the energy equation which is equals to energy at point 1 minus the head of the turbine. So unlike in the pumps, we increase the energy, but here the energy is decreased. Minus head loss again, if we want to consider the head loss, and that will be equals to energy at point 2. So again, same solution for the energies, only that we have negative head for the turbine. So for the output power of the turbine, same solution as with the pump. So multiply the flow rate to the unit weight of the fluid and the head of the turbine. Okay. So let's now apply Bernoulli's equation as well as the energy equations that we have discussed here. So let's answer some sample problems.
Okay. Natapos yung video. So, sample problem para sa fluid flow.
We have here a 300 mm pipe connected by a reducer to a 100 mm pipe. Points 1 and 2 are at the same elevation. Okay, point 1, this is point 2. And the energy lost from point 1 to point 2 is equivalent to 20 kilopascal. Compute the pressure at point 2 if the liquid is water. Okay, so we have a given pressure at point 1. So we have pressure here of 200 kilopascal. Pressure 2 is no. We have the discharge. So let's write the given. Discharge Q is 35 liters per second. Pressure 1, that's 200 kilopascal. And they are on the same elevation. So the diameter of point 1 is 300 mm and will reduce to 100 mm diameter at point 2. So we're going to compute the pressure at point 2. So given also here is head loss, which is in kilopascal. It is in the unit of pressure. So since what we're going to use in head loss should be in the unit of meter, so this pressure should be converted to its equivalent head. So for letter A, okay, the liquid is water. So let's convert first the head loss to its equivalent head. So as we recall, the pressure is equals to the product of the unit weight of the fluid multiplied by the height or its equivalent pressure head. So let's determine pressure head by dividing the pressure by the unit weight of the liquid. So pressure for the head loss is 20 kilopascal. Okay, so we're referring here to the head loss. So we convert that into head, 9.81 kilonewtons per cubic meters. So kilopascal is kilonewtons per square meter. So our unit for the head loss is in meters. 20 divided by 9.81. That's 2.039 meters. So this is the head loss in meters. Now, using Bernoulli equation, we have here the sum of the energy at point 1 is equals to 0.2. But since we have given head loss here, so we have to subtract the head loss on point 1, and it should be equals to the energy at point 2. So energy at point 1, we have the velocity, so velocity head, v squared over 2g, pressure head, pressure head is P over gamma, P1, plus the elevation head, Z, equals to velocity head at point 2, minus head loss equals to velocity 2 squared over 2g plus pressure at point 2, gamma plus Z2. So it is given here that the elevation at point 1 and 2 are the same. So our elevation head will be equal. So they will be cancelled out. So rewriting the equation, we have v1 squared over 2g plus p1 over gamma equals to v2 squared over 2g plus p2 over gamma. So what is required here is pressure at point 2. We can now substitute the given values for velocity. For the velocity, we can determine the velocity at point 1 and point 2 by using the given discharge. So the given discharge is 35 liters per second. So we will convert that first to cubic meters per second, just divide it by 1000. That's 0.035 cubic meters per second. Now, we have an equation of discharge equals to area times velocity. So, for us to determine the velocities at point 1 and 2, we can use this formula. So, it means the velocity at point 1 is equals to discharge over area. So, discharge is always equal at point 1 at going to point 2. They are constant. The discharge is always constant. So here, divide the discharge of 0.035 cubic meters per second by the area, cross-sectional area of point 1. So area at point 1, that's 300 mm. So 300 mm diameter, pi d squared over 4. So pi times the diameter. So that is in diameter. So we convert this first to meters. So 300 mm is 0.3 meters for us to have a consistent unit of meters for the square meter for the area. So 0.3 meter square divided by 4. Okay, let's solve now. Velocity 0.035 over the area, pi d squared over 4. So that's 0.495 velocity meter per second. Okay, so that's the mean velocity at point 1. At point 2, okay, we will just change the diameter for point 2. So velocity 2 equals to the discharge divided by area at point 2. So same. Solution 0.035 cubic meters per second divided by cross-sectional area. So the diameter at point 2 is 100 mm. So that's 0.1. 100 mm is 0.1 meters square divided by 4. Okay. So let's now solve this. Changing this to 0.1. 4.456 meter per second. So yeah. Okay. So the velocity, mean velocity at point 2 is greater than 0.1 because the diameter is smaller. So next, we can now substitute these values at the energy equation. Okay, so I forgot here the head loss. Okay, in the energy equation, we have here head loss minus HL. So let's rewrite that again. V1 squared over 2G plus P2 over gamma minus head loss equals to V2 squared over 2G plus P2 over gamma. Okay, let's substitute. This is P1. Substitute V1 is 0.495 meter per second. We will raise that to 2 divided by 2G, 2 times 9.81 meter per second squared. So, will be added by pressure at point 1 is 200 kilopascal. So, 200 kilonewtons per square meter or kilopascal. Divided by the unit weight of the fluid. So, we have water, we use 9.81 kilonewtons per cubic meters minus the computed head loss. So, 2.039 meters. So all these terms are in meters. It will be equals to velocity at point 2 is 4.456 meter per second. Raise that to 2 over 2 times 9.81 meter per second squared added by pressure 2 plus over 9.81 kilonewtons per cubic meters. Let's simplify the equations. So first, the first term, 0.495 squared divided by 2 times 9.81, 0. Okay, so let's directly add this. 200 over 9.81. So that's 20.3998 meters. So subtracted by 2.039 meters equals to 4.456 square over 2 times 9.81. 1.012 meters plus P2 over 9.81. Okay, so you have 20.3998 meters minus 2.039 minus 1.012 is equals to P2 over 9.81 kilonewtons per cubic meters. So let's solve this. 20.3998, 2.039, and 1.012. That's 17.3488 in meters. So P2 equals to 9.81 kilonewtons per cubic meters. So multiply both sides by 9.81 kilonewtons per cubic meters. We have an answer of 17 or 17.3488 times 9.81. That's 70. Okay. 170.192. That's in kilonewton per square meter or kilopascal. So, pressure at point 2 is 170.192. Okay. So, that's the answer for letter A. If the liquid is water. How about if the liquid is oil with a specific gravity of 0.85? So we have the same solution in letter B. Only that we will just change the unit weight of the liquid. So for letter B, the unit weight of oil is equals to 9.81 times 0.85. That's in kilonewtons per cubic meters. So 9.81 times 0.85, we will use this unit weight, 8.3385 kilonewtons per cubic meters. Okay, so same solution applies here. What will change here are the head loss. So for letter B, liquid is oil. For the liquid, which is oil, we have pressure over unit weight of oil. So that's 20 kilopascal over 8.3385 kilonewtons per cubic. So the head loss for oil is 20 divided by 8.3385. 2.3985. 2.3985. That's in meters. So we will use that here on this equation. So in determining the velocity at point 1 and point 2, so the unit weight will not affect the values for our velocity at point 1 and point 2 since the unit weight is not used in computing the velocity. So just applying Q is equals to AV. So we will just have the same answer given that we will also use discharge of 35 liters per second. So the velocity are the same, so we will not compute that. Let's just rewrite 0.495 meter per second, and the velocity 2 is 4.456 meter per second. So pressure at point 1, same given, that's still 200 kilopascal. And we have a head loss of oil, which is 2.3985 meters. So that's it. Let's apply again. Bernoulli equation. V1 squared over 2G plus P1 over gamma plus Z1 minus the head loss equals to P2 squared over 2G plus P2 over gamma plus Z2, and that's the equation. So Z is cancelled because they are the same in elevation. Next, for velocity 1, substitute 0.495, that's in meter per second raised to 2 over 2 times 9.81 meter per second squared plus P1, 200 kilopascal over 9.81, our unit weight will be unit weight of oil. For the unit weight of oil, we use 8.3385. 8.3385 kilonewtons per cubic meters. Then subtract the head loss, 2.3985. Right? 2.3985. So 2.3985 meters equals to velocity 4.456 meter per second. We will raise that to 2 over 2 times 9.81 meter per second squared plus P2, which is unknown, over unit weight of oil 8.3385 kilonewtons per cubic meters. Okay, so let's directly solve this equation here. So I will directly solve it using the calculator. On the left hand side of our equation, we have here 200 over 8.3385 minus 2.3985. So the answer is 21.599 in meters. Okay, equals to 4.456 square over 2 times 9.81. 1.012 meters equals to P2 over 8.3385. Next, what we will do is subtract 21.599 minus 1.012 equals to P2 over 8.3385 kilonewtons per cubic meters. Okay, let's subtract 21.599, 1.012, that's 20.587 meters. Then multiply both sides by 8.3385 so that this denominator will be cancelled out. So we will have 8.3385 kilonewtons per cubic meters times 20.587. 171.665 kilopascal. That's the pressure at point 2 if the liquid is oil. Okay, this is the answer for letter B. And for letter A, we have 170.192 kilopascal. Okay, next problem.
Okay, so dito na muna magtatapos yung ating video presentation. Okay, class. Again, dito magtatapos yung ating video recorded lecture. So, thank you, class, and see you next video.